Hey kids, what's up? Mr. Murray here, back on Mr. Murray's Mathland, and today we're talking about domain and range, and specifically today from a graph. So when the graph is already in front of you, can you interpret the domain and range? And we are going to focus on using interval notation to describe each of those. So a little practice there. And in case you are a little rusty here, domain is the set of all x values or input values. It doesn't always have to be x. It could be, t or for time or theta or, if you get into trig. But that's your input and your range is your output. Or most times you'll say the set of all y values, right? Okay. So for all of these, I said we're focusing on the graph, but I've also presented the equation with each one. One so you can maybe even brush up on, your shapes of graphs based on the equations, some functions you might be familiar with, but also so you might start to make some connections between the domain specifically and the domain of the graph that you see. And because then another video we're going to have is just getting domain purely from the equation. So here we go. Number one, we have a parabola. Hopefully that's pretty familiar to you. A parabola, and it's in vertex form here. We can see that it's been shifted 3 units to the left and 1 unit down. So there is its vertex at -3, -1. And it's opening up. If there was a negative out in front here, that would flip it upside down, make it open downward. But now let's talk domain and range. Okay. So the domain, as you might recall from any parabola, any sort of quadratic function here, is all real numbers. And you can see this, that if you were looking at this graph and you kept zooming out, this graph is going to keep going to the left, to the left, to the left, to the left, and to the right, to the right, to the right, to the right. So every x value is going to be sort of achieved by this graph. You just have to keep zooming out, and it's going to keep expanding to the right and to the left, slowly and slowly. So the domain of all real numbers but we're going to express that with interval notation. So all real numbers means everything on the number line from -infinity to infinity. So, and there we go. There's really what we're looking for, -infinity to infinity. That means all real numbers. Now your range, you're trying to describe these y values. So now think about the y-axis visually. Does the graph, and here's where -infinity is on the y-axis, and here's where positive infinity is. Does the graph go down to -infinity? No. In fact, so when you want to start chronologically, like when you use interval notation, start at the bottom where -infinity is and kind of come up and say, is the graph defined yet? Is the graph defined yet? Is the graph defined yet? The first time it's defined, the first y value where this graph exists is at -1. And then the graph exists for all y values after that. The graph keeps going up, 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 up. So it's going to, achieve every y value beyond that. So sometimes as practice, if you're still getting the hang of interval notation, you might write it with inequalities first and say all the y values on this are greater than or equal to -1. And that's what you're focusing on there. But with interval notation, that would mean from -1 inclusive, so using the bracket, to positive infinity. And remember, infinity always gets parentheses around it, or -infinity. So -1 inclusive to infinity. And there we go. So let's take a look at a couple more examples here. I've actually got a handful here, a good variety. This is a square root function, if you like, square root function, which normally, kind of looks like a half of a sideways parabola. And it has been shifted 5 units to the left and 2 units up, similar to, vertex form, but your transformation rules. and a negative out in front has caused it to be, instead of opening kind of up like that, flipped upside down, a reflection. So again, here is just to highlight this point, the sort of vertex of that curve. It's at -5, 2. And now to do your domain, now you're focusing on that x-axis, right? X values. And the graph does not exist to the left, all the way to the left. And it does not start existing until you get to -5. And once you get to -5, that's the first x value where it exists. It exists everywhere to the right. You know, the graph keeps going to the right, to the right, to the right. It exists. So this graph exists for all x values greater than or equal to -5. There's the inequality of it. And what is that in interval notation? -5 inclusive, you know, with a bracket, to infinity. Now for the range again, think of the y-axis here, right? And the y-axis, -infinity is at the bottom, infinity is at the top. You always start at -infinity because you're going chronologically. Does the graph exist at -infinity? You know, does it have y values that go down to -infinity? And yes, it absolutely does. The graph is going down kind of slowly, but it is going to keep going down, 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 down. So it does go down to -infinity, and it will have every y value from -infinity up to and including 2. But that's sort of the last y value it will have, or the greatest y value it will have. After that, it will never go above that. So all the y values are less than or equal to 2. And so how do we describe that? From -infinity to 2 with a bracket. So -infinity to 2 inclusive. So again, when you're looking visually, doing domain, start at the left, that's where -infinity is, and look to the right. You know, does the graph exist? And if not, when does it kind of start existing? And then look to the right. When you're doing y, the range, you start at the bottom, that's where -infinity is on the y-axis, and you come up and ask yourself, does it exist? If not, when does it start existing? When does it stop existing? And that's it. So let's just see a few more here and keep brushing up on these little review of functions. We have an exponential function here, e 2.71828, etc. And you may notice that that would be an exponential growth, a base bigger than 1, but a negative out in front has caused a reflection. So now it's going down like that. And the -2 has shifted it down 2 units. All of that's really extra here. You don't need to know that to do the domain and range because the graph's right in front of you. But for your domain, again, start at the left, right? That's where -infinity is on the x-axis. And does the graph exist at -infinity? Yes, definitely. And as you go to the right, does the graph keep existing? As I go to the right, as I go towards infinity, yes, this graph will exist. This is just going down so sharply that you don't see it over here, but you know that it exists. It keeps going to the right very, very slowly if you kept zooming out. And that's a little review of our domain from an equation, perhaps to kind of bolster that when you talk about domain, you're really saying, are there any x values where this thing would not exist, where this thing would be imaginary or undefined? And with an exponential, you could plug in every x value, any x value you want, and you'll always get out a real number. So the domain is all real numbers, or from -infinity to infinity. The range, -infinity to infinity on the y-axis. Start at the bottom, start with -infinity. Does the graph exist down here? Yes, it definitely does. It's going down to -infinity, and it has all these y values up to, but not including 2. And that is, as far as it goes, does not go beyond 2, or sorry, -2. And you may recall that because there's a horizontal asymptote at y equals -2. And that's what this dashed line is trying to show you, that there's kind of that boundary. So our range goes from -infinity to -2, but since we don't actually get to -2 because of that horizontal asymptote, it is -2 exclusive, so with a bracket, or excuse me, with a parenthesis around it. Okay. And hey, if we're going to look at exponential graphs, why not look at their inverses? A log graph, specifically a natural log, which is a base of e, and they're kind of they're the inverses, so they're not kind of, they are the reverse of an exponential graph, that they have a vertical asymptote. So when you talk about domain, there are restrictions on the domain. Does the graph exist at -infinity? No, it does not. When does it start existing? Just on the other side of this vertical asymptote of x equals -3. So this exists from -3, and then the graph does go to the right, to the right, to the right. It does exist to infinity. And it does not include an x value of -3. So we use the exclusive parenthesis there. And you may recall that if this is not about reviewing your log properties, but if you were to plug in -3 here to this function, you would get -3 plus 3, you'd get 0. And then the log, or specifically natural log, of 0 does not exist, because that's like saying e to what power gives you 0. And you would never get 0 out. So the inside of a log always needs to be positive. The argument, as they call that. The range, now that we're talking range, talking y values, does the graph exist at -infinity? Yes, this curve does go down, 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 down. And does it go up? Is there any sort of end to its y values? Is there any maximum y value? No, this is going to keep going up slowly, 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 but it is going to go up. So from -infinity to infinity, all real numbers there. And you'll notice, just to compare it with the previous problem, that the domain on an exponential is always all real numbers. That's always the range on a log graph, these basic exponential, basic log graphs. And, x and y have been flip-flopped, so that means domain and range get flip-flopped. And the range is not all real numbers, just as the domain is not all real numbers here. Vertical asymptotes and horizontal asymptotes. All right, so now that we're talking about asymptotes, let's talk about some rational functions here, which will frequently have both vertical and horizontal asymptotes. And this graph that's in front of you, again, you don't need to remember anything algebraically yet, but your domain, does the graph exist at the left? Yeah. All the way to -infinity? Yeah, the graph exists, the graph exists, the graph exists. Is there any x value where it stops existing? Right here at x equals 3. The graph does not exist. But it does exist on the other side of 3, right? And it goes to infinity, as we are led to believe from here. So it exists for every x value except that one value of 3. So x is anything or all real numbers except 3. So how do we describe that with interval notation? It exists from -infinity right up to, but not including 3. And then just on the other side of it, from 3 to infinity. So you could use a union symbol in between those two groups, but it's not necessary. You could use a comma if you like. But this is showing basically every x value except 3. And that's what's happening here. That's kind of showing you're excluding it on both, both sides of it. You're taking it out of the domain. And your range is a very similar thing. The graph does exist down at -infinity. It exists, it exists, it exists. But where does it not exist? It does not have a y value of 1. There's a horizontal asymptote there, but it does exist on the other side of that. So everywhere except at y equals 1. And so very similarly, we're going to say from -infinity to 1, exclusive, and from 1 exclusive to infinity. It's like just skipping over that one single value. And there we go. And if you want to make some connections to the equation here, why couldn't x be 3? Why is there a vertical asymptote at 3? Because look what happens if you plug in 3 for x. You get 3 minus 3, you get 0 in the denominator of a fraction. That's undefined. And the y value of 1 comes from this right here. Okay. Now let's see, this is a slightly more complicated rational function. You'll notice there are 2 vertical asymptotes here. So the graph exists from negative infinity. It's good, it's good, it's good, it's good, it's good, it still exists, but it does not exist at this x value, and it does not exist at this x value of 3. There's another vertical asymptote, but it does exist everywhere in between. We've got this curve down here. So it exists everywhere in between, and it exists everywhere to the right. So all real numbers except for these 2 individual values, everything in between, everything to the left, everything to the right. You're basically just saying any x value other than -1 or 3 is good. So how do I describe that with interval notation? From negative infinity to -1 exclusive, and then from -1 to 3 to describe that middle region. Everywhere between -1 and 3 it exists. And then from 3 to infinity. So you see 3 pieces to the graph, 3 regions to the graph, 3 intervals where the graph exists. Its range, you will notice that there is a horizontal asymptote. You can see the graph is flattening out at y equals 0. And so when you come up here, though, be careful. You know, when you come up from negative infinity, the graph does exist, it exists, it exists, it exists, but it stops right there. It has a maximum y value of -2.25. That's the highest y value that that portion of the graph achieves. And then it does not exist again until you get to 0. And it doesn't actually get to 0 because it's a horizontal asymptote. But then it has all of these y values as you go up the y axis here. It's going to have all those y values. So you see what I've basically done? It's almost like I've kind of drawn interval notation, or drawn that number line, just drawn it vertically from negative infinity, -2.25, and it does get it, so including that value, excluding 0 to infinity. So that would be from negative infinity to -2.25, and including that value, because it does have that as a y value at that maximum right there. And then from 0, but exclusive, so with a parenthesis, to infinity, right? Because based on what we see, it does not look like this ever actually has a y value of 0. So you got to use the parenthesis there, the exclusive. And you may recall those kinds of things, you know, those rules, but that's not really what this is about. -1 and 3 are what will make the denominator be 0, and that's why it's undefined. The degree of the denominator is bigger than the degree of the top. That's why there's a horizontal asymptote at 0, but whatever. You'll get into that when you cover your rational functions unit. This is just about the interpreting. And here's one more, a classic conic section. In this case, an ellipse, and it's a vertical ellipse because the bigger denominator is under the y quantity. The center of it, as you can see from the graph, just for a little review, is at -1, 3, and that could be seen by looking at these values, right? Take those opposites, -1, +3. There's the center. This right here is 4. The square root of it is 2. That shows you that kind of horizontal distance from the center to those endpoints of what we call the minor axis. Square root of 25 is 5. There's that distance out, or half of the major axis is 5 units in each direction vertically. But what's really important here is just can you look at this and determine the domain. And so the graph does not exist at negative infinity, but the first time it does exist is right here at -3. And it does actually get that value. So that does exist. And where does it kind of stop existing? When x is +1. That's the biggest x value it ever has. So from -3 to +1 and inclusive on both sides. And that's it. There are no x values outside of that interval for this graph. And the range, very similarly, does not exist at -infinity, but starts when y is -2, and exists, has all these y values, but the greatest y value it ever has is +8. So that would be from -2 to +8, inclusive on both sides, so double brackets, and there we go. There's our domain and range. And so that was a lot of different examples just to try to show you a variety there, but you'll never see every example. But it just tried to show you a handful in case you were like wondering, well, what if it looked like this? What if it did this? So I tried to show you a variety, but maybe this was a long video. But hey, if you're watching it, you care. So if you have any questions, let me know, and hang in there and keep working hard.